everyone, for today's lesson we are going to learn about how to write explicit rules for not only arithmetic and geometric sequences, but also neither sequences. Before we get started, I would like you to please go ahead and factor these two expressions. The first expression is x cubed minus 4x squared minus 10x plus 40, and the second one is 5x to the fourth power minus 4x squared minus 1. Please factor each, pause the video as you do it, and then restart the video and we'll see how well you did. Okay, so the first thing that we want to do is we want to recognize the fact that this has four terms. So we want to put parentheses around the first two terms, change that minus sign to a plus negative, and then put parentheses around the last two terms, leaving the plus sign in the middle. Then I'm going to identify the greatest common factor between these two terms, and I end up with an x squared, and my leftovers is an x minus 4. Plus, the greatest common factor between negative 10 and 40 is going to be a negative 10, and my leftovers is an x minus 4. Then I'm going to write a parenthesis of my outsiders and my insiders, and I end up with x squared minus 10 times an x minus 4. And that is my answer. Notice that just because that there are two x minus 4s that I don't have a squared right here. That seems to be a common error that a lot of students make. So if that's something that you've noticed that you're doing, please make sure that you make that change. Let's go ahead and look at number 2. For number 2, we have ourselves a quadratic form. And so I'm going to split apart the 5x to the fourth power into a 5x squared and an x squared. And then I have to look at the factors of 1. Well, there's only one factor of 1, and that's 1. So let me go ahead and we want to make sure that we end up with a negative 4. So I know that 5 times 1 is 5, and 1 times 1 is 1, and I want a negative 4. So that means that my 5 needs to be negative, and the 1 needs to be a positive. Now, x squared minus 1, that is a dot. That's a difference of two squares, so we can factor that even further. So we have 5x squared plus 1 times x plus 1 times an x minus 1. And that is your factorization. Hopefully you did pretty well in factoring. Remember that factoring is going to be on our last test as well as on our final exam, so please make sure that you feel comfortable with factoring. And if you don't, always make sure that you come and see me after school sometime so that we can talk about factoring. Let's go ahead and look at our learning objectives for this lesson. So our learning objectives is for you to be able to say, I can determine whether a sequence is arithmetic, geometric, or neither, and I can write an explicit rule for the sequence. So the key word here is explicit rules. So we're not writing recursive rules, explicit rules. So some of these rules we already know. So we know that when it comes to arithmetic, arithmetic mirrors a linear function, and our explicit rule is written in the form of a sub n is equal to d times n plus b. We also learned about geometric. Geometric sequences, if we were to write an explicit rule, it mirrors an exponential function, and that is a sub n is equal to a sub 1 times r to the n minus 1 power. So now we're going to be talking about neither sequences and writing an explicit rule for it. So for these types of rules, you have to think. Some of them are going to be more obvious than others, but you really have to think. You have to look for connections with the position number. Look at perfect squares. Look at perfect cubes. Maybe think about factorials. There's a lot of different things that you need to look at. Look for patterns. Maybe you'll have like it'll be related to linear functions. There's a lot of things that I need you to look for. But whenever it comes to explicit formulas, you're going to have a sub n is equal to something related to n. You're going to have some sort of n involved in your problem. You are not going to be working with a sub n minus 1, and you will not be working with a sub n minus 2. So please just keep that in mind. Let's go ahead and look at letter A. For letter A, we want to write an explicit rule for the sequence. Woo. There we go. Right. There we go. So we want to write an explicit rule for the sequence, and we want to remember to check to see if it's arithmetic or geometric. So from the very beginning, I'm going to write arithmetic, geometric, or neither. And so I'm going to decide from the very beginning what type of sequence I have. So going from 1 to 4 and 4 to 9 and 9 to 16, I'm not adding the same number each time. I'm not subtracting the same number. It looks like I'm not multiplying. But what I do see is that 1, 4, 9, and 16 are perfect square numbers. So what I'm going to do is I'm going to put in just above each of these values the position number. So I have 1, 2, 3, and 4. And I know that 1 squared is 1. And 2 squared is 4, and 3 squared is 9, and 4 squared is 16. So this tells me that this is a neither sequence, and what I'm doing is I am taking my position and I'm squaring it. My position squared, and that's how I'm able to come up with these numbers. And that is my explicit rule. A sub n is equal to n squared. Let's go ahead and look at letter B. For letter B, what we want to do is we want to look at our value. We want to identify if this is an arithmetic, geometric, or neither. We need to look at our numbers. I know to go from 2 to 4 to 6 to 8, it appears as if I am adding 2 each time in order to get to the next value. And that tells me that this is arithmetic. So if this is arithmetic, I know what my common difference is. My common difference is 2. So if I want this to be written as an arithmetic rule, that means that I need to write it in the form of A sub n is equal to D times n plus B. I know my D, my common difference. I'm adding 2 each time to get to the next value, but I need to work with an ordered pair. I'm going to work with the number 2, and that ordered pair is going to be 1, 2, and that's because the number 2 is located in the first position. So this number 1 represents my n, and this number 2 represents my A sub n, and I'm going to substitute those values into the formula to find B. So I'm going to write 2 is equal to 2 times 1 plus B. 2 times 1 is 2, and I'm going to subtract 2 on both sides, and I end up with B is equal to 0. So my formula is going to be A sub n is equal to 2 times n plus 0, which is just 2n, and there is my explicit rule. Let's go ahead and look at letter C. For letter C, we want to decide, is this arithmetic, geometric, or neither from the very beginning. So I'm going from -3 to 9, from 9 to -27, -27 to 81. Make this out a little bit so it's clear. And it appears as if in order to go from -3 to 9, I'm multiplying by -3. And to go from 9 to -27, I'm multiplying by -3. So because I'm multiplying by -3 each time in order to get to my next value, that means that this is geometric. And my R value is equal to -3. So now I'm going to be working with the form A sub n is equal to A sub 1 times R to the n minus 1 power. I know what my first term is. That's -3. It gives it to me right there. So I can write this formula as A sub n is equal to -3 times -3 to the n minus 1 power. But unfortunately, because these two numbers are the same, we actually have to clean it up a little bit more. This is one of those problems that we call a special case. And then what makes it a special case is the fact that our first term and our R value is the same. And if that's the case, then what we have to do is we have to add our exponents. So whenever you're multiplying two powers with the same base, we add our exponents. So adding my exponents means that I'm going to be writing this as A sub n is equal to -3 raised to the 1 plus n minus 1 power. 1 plus n plus -1, these two 1s are going to cancel out, and we end up with our form being A sub n is equal to -3 to the nth power. You will see something like this in your homework. Please be prepared for seeing a problem like this, and be prepared for seeing an answer written in simplified form. So I just wanted you to be aware that there exist problems just like this in your homework. Let's go ahead and look at letter D. For letter D, I have 1 over 4, 1 over 9, 1 over 16. Well, clearly we're not going to be multiplying or dividing the same number each time to get to the next values. We're certainly not adding or subtracting, so that tells me that this is going to be a neither situation once again. And I know that whenever it's a neither, one strategy is to put your position numbers just above it. So I'm going to put 1, 2, 3, and 4 just above my values. And I know that I can change this 1 to being a 1 over 1. So I really have 1 over 1 squared, that's going to equal 1. 1 over 2 squared, that's equal to 1/4. 1 over 3 squared, that's equal to 1/9. And 1 over 4 squared, that's equal to 1 over 16. So what is my rule? Well, in order for me to come up with my next number, what I'm doing is I'm taking 1 and I'm dividing it by my position, which is n, squared. And that is my rule. Letter E we are going to do in class. Feel free to try that one on your own if you would like. But let's go ahead and look at letter F. For letter F, I have 1, 1/8, 1 over 27, 1 over 64. And it doesn't appear as if we're adding the same number each time in order to get to the next value. It doesn't appear as if we're multiplying because 8 and 27 and 64, they're not all really related to one another, so it's not geometric. Once again, this is a neither situation. So I'm going to put in my positions because that seems to be pretty helpful to put in the positions and trying to find a relationship. So I know that 2 and 8, if I were to cube 2, I would end up with 8. And if I were to cube 3, I would end up with 27. So this is what I see. I see 1 over 1 cubed, that equals 1. I see 1 over 2 cubed, that equals 1/8. 1 over 3 cubed, that is 1 over 27. And 1 over 4 cubed, that's equal to 1 over 64. So what is my rule? Well, it appears as if in order for me to come up with my next number, what I'm doing, or each of our values, it looks like I'm going 1 divided by my position cubed. And that is my rule. Letter G we're going to do in class next time I see you, as well as letter I. Feel free to try both of those on your own. Let's look at letter H in the last example of this set of discussion notes. For letter H, we have ourselves 2 over 1, 3 over 3, 4 over 5, 5 over 7, 6 over 9. Well, it doesn't appear as if we're adding the same number each time, so it's not arithmetic. In terms of multiplication, going from 2 to 1 to 4/5, we're not multiplying the same number each time in order to get to our next value. So once again, this is a neither situation. So for this type of problem, you really have to kind of analyze the patterns. Maybe look for a pattern in the numerators or the patterns in the denominators. So if I were to split this apart into maybe 2 pieces, just looking at the numerator and just looking at the denominator, I noticed that to go from 2 to 3, I'm adding 1, and 3 to 4, I'm adding 1, and 4 to 5, I'm adding 1. And 5 to 6, I'm adding 1. So it looks like I'm adding 1 each time in the numerator. And in the denominator, it looks like I'm adding 2 each time in order for me to get to my next value. So that's very interesting as well. So that's a pattern that I'm noticing. And I'm going to write down that pattern because that's what I see. Okay, so I'm also going to write down the position because whenever I've worked with neithers, I know that the position has helped me. It doesn't always help you, but sometimes it'll help you. So I can see that this is the first position, the second, third, fourth, and fifth. So let me see if I can come up with some kind of way for me to come up with a numerator and a denominator. Okay, so I can see that in order for me to go, like for my numerator, 1 to 2, 2 to 3, 3 to 4, 5 to 6, I'm sorry, 3 to 4, 4 to 5, 5 to 6. It appears as if I'm taking my position and adding 1 to it in order to come up with my numerator. So like 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5, 5 plus 1 is 6. That works. So just working with my numerator, I can say so far that a sub n is going to be equal to some kind of fraction, and I'm going to take my position and I'm going to add 1 to it. So that's what I see in my numerator. My denominator is a little bit different. So how can I go from looking at my positions? I have 1 and 1, and I want to get to 3. How can I work with that? So, and then I have 2 to 2, 3, and I want it to become a 5 and a 7 and a 9. This one's a little bit trickier. So what I can do is I can just rewrite just the denominator. So some of you might be able to see this pattern right away. So I'm just going to work with my denominator, 1, 3, 5, 7, and 9, and I know that my common difference is going to be a 2. So if I were just to work with the denominator, I know that my common difference is equal to 2. If I were to write this as an ordered pair, like the number 1 is an ordered pair, I can write that as 1, 1. And because my common difference is 2, and I can tell that this is going to be an arithmetic sequence in the denominator, I can just come up with my rule working with what I know about arithmetic sequences. I can write my denominator in the form of a sub n is equal to d times n plus b, because I know that some version of that's going to go down here. So I can let n equal 1 and a sub n equal 1 and d equal 2, and I can find a b value. So I'm going to write 1 is equal to 2 times 1 plus b. I'm going to subtract 2 on both sides, and I find that b is equal to -1. So what's my rule? Well, that would be a sub n is equal to 2n minus 1. So this 2n minus 1 is going to go down here in my denominator. And that is my rule. 2n minus 1. Let me see if that works. So 2 times 1 is 2, and 2 minus 1 is 1. Okay. 2 times 2 is 4, and 4 minus 1 is 3. 3 times 2 is 6, 6 minus 1 is 5. So it does appear to work. So cool, I have just figured out my rule. So sometimes it might be beneficial for you to break apart fractions into two different pieces in order for you to figure out what your rule is going to be. That is the end of this lesson. If you have any questions over anything, please feel free to email me. Also, once again, please feel free to try the your turns on your own. We're going to talk about them in class, but if you wanted to get the extra practice of thinking beforehand, that might be a good thing. Otherwise, I will see you next time.